Howdy, AP PreCal. It is Miss Kosh. Today I want to look at topic 2.6. It's called Competing Function Model Validation. Basically, they have added residuals into the PreCal curriculum, and it's kind of a new area for us. Last year was our first year with the course, right? And I went to one of our AP stats teachers on campus and said, help. So I'm better at it this year perhaps than I was last year, and anyway, he was very helpful. But I did want to go through Mr. Passwater's notes on residuals. So to be honest with you, once again, I haven't had a chance to look at this ahead of time, but hopefully I know enough of what I'm talking about that this will be beneficial. So let's jump in. Okay, so we have seen different kinds of examples of data sets that we want to model with some sort of an equation. So we've seen things like you might have a situation where the arm span and the height of a person could be modeled by a linear function. So sometimes if you find a bunch of people and you measure how tall they are and measure how long their arms are, you'll find that tends to follow a linear correlation. Okay, you might find something where you look at what would be quadratic. Well, it would be quadratic like this if you look at the height as something as a ball is being kicked, you measure the height and it goes back down. What else might be quadratic in the real world? Well, that's the best example. Or you can find the area. Area functions, like if you're trying to figure out how much fencing, I have this much fencing and I need to put it, I have this side of a building and I've got this much fencing to go on, how can I maximize the area? Area functions are quadratic. You have things that are exponential. So we look at population levels or we can look at half-life of different radioactive things. You can talk about the bacteria is growing at an exponential rate. You can talk about a disease is spreading through a community at an exponential rate. There's a whole lot of examples of things that become exponential. And so it says on the AP exam, students will be expected to determine which model is most appropriate given a set of data. There are a few strategies. Okay, so a linear function has, so here they gave us a table. Use a linear model when the data reveals a relatively constant rate of change. So there's situations, we have some scenarios where everything falls exactly on the line and you're going to have something that's exactly a constant rate of change, and that would be linear. This is saying it's relatively constant. So we could kind of look and compare the rate of change as we go down, and we'd find that it's pretty close. And you'll notice that these points are kind of above and below the line just a little bit. But it's obvious that the best way to model those points would be to draw a line straight through it. We could also see, if they say use a quadratic model when the rates of change are increasing or decreasing at a relatively constant rate. Okay, so once again, it may not be perfect. Some of these points are a little bit off the curve, but you can see that they follow that shape. Data generally following a U-shaped pattern. So a U like this or a U like that would typically be quadratic. Okay, an exponential model is what we want to use when the output values are roughly proportional. Each successive output is approximately the result of a repeated multiplication. Okay, so maybe the ratio of these numbers is, if the ratio of these numbers is somewhat, my brain just stopped. If the ratio of these numbers is proportional or relatively proportional, then it would match the form y equals a times b to the x. If we find that the rate of change is proportional, then it might match the format y equals a times b to the x plus something. So we might have shifted things up. But the calculator regression lives in that world, so okay, here we go. Let's see the problems that he suggested. So select values from several functions are given in the table. Sketch a scatter plot for each. Determine if it's linear. Okay, so 0, 11 is here. 2, 8.4 is, well, hopefully right about there somewhere. 4, 5. I don't know. Is this beneficial to you to watch me struggle? Yeah, don't ever get old. It's not any fun. My eyes don't work like they used to. 6, 2.3. I mean, I'm not old. I refuse to be old. 8, -1 would be down here. That appears to be linear. I think that's the extent of what he's wanting us to do. I'm bleeding through the paper. Here we go. The next one, -1, 2 is somewhere here. 1.5, 5.5 is somewhere here-ish. 4 is 10.5. 10.5, where's 4? 1, 2, 1, 2, 3, 4. So somewhere here. Okay, then we're going to come back down. 6.5 and 5 so somewhere over here. Well, this appears to, and then 9 is going to be 2.25, so something like that. That appears to be quadratic. Okay, that was linear. This is quadratic. I don't know, is this beneficial to you? Anyway, 1, 10, 3, is that 5 something? So 1, 2, 3, so somewhere about here. 5 was at 2 point, so here's 5, a little over 2. 7 is, okay, this appears to be 9. So notice this is starting to like decrease pretty quickly. This I would say would be an exponential. In particular, it's an exponential decay. -2, 2, 1, 3, 4, 4.5, 7. We're a little lower than 7. Where is 7? Somewhere about here. I don't know. What is this? This is looking 10, 10. This is looking pretty linear-ish. Well, not anymore. Maybe this is exponential also. Okay. Oh, that was fun. Okay, so residuals. When we create a model, we can use our model to predict values for a dependent variable, given an independent variable. When using a model, it's important to remember that this is only a predicted value. Okay, so basically what's happening here is, and we've done this already in class, we've done this a bunch. Like, what would you expect if this is, like, we draw that perfect line? That is not the correct answer. But then we would look to say, okay, well, that's what we would expect at 3. I can use this line to make a prediction. Find the output value when my input value is 3. It's roughly 6. Okay, not perfect, not drawn to scale. I'm just trying to give you the idea. Okay, if we use the input value from the known data point and find if we use the input value from a known data point to find a predicted output value, the difference between the actual output and our predicted output is called the residual. So it's the actual value. So what was it in the table versus, so this is on the table, in the chart, whatever you want to say. The predicted value, it came from the graph. It came from the model. Okay, so if they gave us, so for example here, if they gave us 3, and this is h. H of 3 is actually equal to 5.2, but say in our model, we call that, I like the letter K. K of 3 gave us instead 6. I'm just making up numbers. Then the residual would be the actual value from the table, and then the number that minus the number that we got from the equation. Okay, hopefully this is somewhat clear. Okay. He continues with his notes. The weight of newborn babies can be modeled by a linear function for the first 4 months after birth. Selected values are here. Use the regression capabilities of your calculator. Okay, so let me find a calculator. I'm gonna clear the memory just so that we start, you see where what did I do? Okay, so I have my Casio, it'll work in TI. I think I've shown you some of those, but for the sake of time, I'm just going to do one. So we always enter in the statistics, same with TI. I have, if I make mistakes and type something in wrong, would you comment below and tell me nicely? Well, no need to add animosity to the world. There is plenty of that already. But I'm trying to be accurate. Okay, so here's that. I can graph this. There's my data. I can calculate the linear regression. And then with my calculator, my kids were struggling with this recently again. They'll hit copy and they'll think that it's there. On the Casio, you have to hit the execute button before it, and then come back to the screen, then you can draw it. And so here it is. Okay, so use the regression. You know what? I don't feel like writing that down, but there it is. It's 0.8x plus 3.34. See where those numbers came from? Super. Okay, and if you notice when we draw that, you can see that the points are, I mean, it follows the shape of that line, but they're not on that graph. Okay, use the model found in part A to predict the weight of this baby at 2.5 months after birth. Okay, I'm gonna come menu, not run matrix, what am I doing? Menu, graph. Okay, so here I can select that one. Do you see how I had to hit select? And then I can draw that. And now I can G-solve and do YCal. Because my time, so I'm at 2.5 months after birth, it is They expect them to be 5.34, I don't know, pounds, kilograms. I don't think in terms of kilograms. I have no idea if that's heavy or not. The actual weight was 5.5. What is the residual? So if you remember, to find the residual, we do the actual minus the predicted. The actual, no, what was the actual value? I lied to you. I always get confused on this. The actual weight was this. Okay, so it's 5.5 minus what we predicted right here. And so what is that? 0.16? So what's the residual? So it's 0.16. Was it an overestimate or an underestimate? Underestimate or overestimate? We underestimated. So we expected the baby to weigh 5.34, and instead it was 5.5. Did our model underestimate or overestimate? Okay. I think that's good. So let me show you while I'm thinking about it real fast. We can, I did this last year. I think I can go to setup. Y'all, I'm going to have to go back and watch my own video from last year. I think there's a way I can turn on residuals. Did we see residual anywhere? Maybe it's, hang on, let's see, menu. You get to watch me struggle. Setup here, does it let me set up? Residual list, ha ha, I remembered, okay. I had list 1 was the independent variable. I had list 2 was the dependent variable. So what I'm gonna do is I'm gonna make list 3 my residual, okay? And so now, when I graph this, here I can graph, that's my graph that we just saw a second ago. I can calculate that linear regression, that one. I don't know that I need to copy or draw it, but now when I come back and exit out, I now have a data that I did not enter. Do you remember? I cleared my calculator. This list right here is the residuals. So each of these, it's showing me how far above or below I am from the value that was calculated by that line. And it found it for all my data points. Okay, so what I can do is I can set my second graph. I'm going to keep the first graph to be my graph, the line, the actual data points. I want my second graph to use the same input values, but now my output values, instead of my output values, I want my residuals. So I'm going to hit list 3. So now it's graphing X versus the residual. So my other graph, so here, let's exit. My graph 1, set graph 1 is the input and the output, okay, which is what I want. And then graph 2 is the input value with the residual value. And so now, exit, I can graph 2, and it's giving me those points. Okay, and it's, in general, when we find that, that it has a pattern to it, we would say that that's not a good model to use. But let me keep going through his notes. So it did look linear, but this does look a little too uniform. So here we go. Okay, a residual plot shows all the residuals for the set of data and can be used to help determine if a model is appropriate for a given set of data. If a model for a given set of data is appropriate, the residual plot should appear without pattern. Okay, so that's how we know it's a good model, is if the residuals are kind of randomly scattered. If we can see a clear pattern in a residual plot, then the model used for the regression was not appropriate. So if there's a clear pattern, I would argue that this kind of was a clear pattern. But here we go. We'll have to ask our stats teachers. Okay, I did figure out how you can get Desmos to do this. So I made a video yesterday. It's a quick 2-minute video about how to get Desmos to graph your residuals and stuff. So that's very exciting. Okay, his notes continue and say, an exponential regression was used to model a data set. The residual plot for the exponential regression model is shown above. Which of the following is the best conclusion about the appropriateness of the exponential regression model based on the corresponding residual plot? Okay, the exponential model is not appropriate. To me, okay, here's what I see. I see that it looks scattered, and so I think it would be appropriate. So, but we know it will be appropriate if there is no pattern. Okay, so it's not appropriate. Hang on, the exponential model is appropriate because it shows a pattern. We don't want it to show a pattern. So that's automatically wrong. the exponential model is not appropriate because it's not appropriate because it shows no pattern. No, we want no pattern. Does that make sense? Those two will always be wrong. And so now we're going to look back at our data set because a pattern means it's a bad fit. No pattern means that it was a good model. So this exponential is not appropriate because it shows a pattern. I don't think it shows a pattern. So I would say I would answer that with C. Okay, a group of AP Precalculus students use a set of data to create linear, quadratic, and exponential regression. After creating the three models, the students created a residual plot for each of the type. Based on the three residual plots above, which model was most appropriate? I see a pattern, I see a pattern, I don't see a pattern. So I would say that one. Give a reason, there's no pattern. Okay, Mr. Passwater, yay, hopes to make it into the Guinness Book of World Records by painting the world's biggest mural on the side of several downtown buildings. Have fun. His mural will consist of many painted circles of various sizes, where each circle is painted in a different color. He wants to create a model to determine how much paint is needed in quarts for the radius. Oh, should he use linear, quadratic, or exponential model? Well, I would imagine if you're comparing radius to area, so you're going to figure out the amount of paint based on the area. That's a square situation. The radius, it's because it's pi r squared is the area of a circle. Let's see. Am I interpreting this correctly? If you don't think I'm interpreting this correctly, comment down below. Should he use? I would think he's going to use a quadratic regression because the variable r is getting squared. So as your r increases, the area is going to increase. The rate of change the area is changing is increasing at a constant rate. Oh my goodness. The second difference will be constant. Anyway, I'm sorry. After creating his model, Mr. Passwater used it to purchase different special paint colors. In this situation, do you think it is more appropriate for the model to underestimate or overestimate the actual amount? I think that it's better for him to, you wouldn't want too much extra paint, but if you don't buy enough paint, then your mural sucks, and then you have to go figure out how to get more paint, and you've stopped the project. So as the model, I would think that he would want the model to overestimate the actual amount so that he doesn't go. But then also, if you're struggling financially, you might want it to be an underestimate so that you can get really close to the amount but not have any paint left over and go buy a tiny bit more if you need it. I don't know, whatever, it depends on your perspective. Sometimes when you're in the middle of a project, you just want to be done and you don't care if you have a little extra paint left over. So anyway, I hope this was helpful. Yeah, it's interesting to add residuals to PreCal, but I imagine it will show up a little bit on the multiple choice on the AP exam. And yeah, good luck. Go practice. Like, subscribe, comment, all the things.